Math 230, Cuesta College. I'm Joe Vasta, and we are covering section 7.4 today, Complementary Probability. This is our last section that we're going to cover. So our last new material is this lecture. So let's go ahead and see what this is all about. Before we do that, here are some puzzles. Fill in the missing box. Another puzzle. Fill in the missing box. And the last puzzle that has to do with probability is this. You're in a room with 30 people. What is the probability that at least 2 of these people have the same birthday? Okay, so there's 365 days in the year, 366 if you count the leap year. How likely will it be that 2 of these people share the same birthday, like March 5th, and then another person has March 5th? Now there's only 30 people, so we'll get into these puzzles at the end. Let's go ahead and talk about complementary probability. What is it? Our box contains 3 red marbles and 1 blue marble. You're going to randomly draw 1 marble out of the box. So the first question comes from the basic probability section. What is the probability you draw a red marble? Well, there are 3 red marbles in the box out of 4. So the answer is 3/4. Okay, the next one, question number 2, what is the probability you draw something that is not red or non-red? Well, we have 1 non-red in the box. That's 1 out of 4 marbles total in the box. That's 4. So these probability problems didn't seem too difficult. But what we want to do is we want to label these 2 events. So when we say you can pull out a red here, and then over here we say you can pull out something that is not a red, that covers all the things that can happen. So these are called complementary events. So this guy right here, that guy right there. And we heard the word complement before in set theory, the complement of a set, which also we can say this is sort of the negation. We have you pull out a red, here's the negation of you pull out a red, you do not pull out a red. Okay, so those are complementary events. And when you look at the probability of complementary events, look at those probabilities there. Those probabilities are called complementary probabilities. So I'll write that down. So take a look at those complementary probabilities. You might pause the video if you want to think about them, but there's some property of those complementary probabilities. The property is that complementary probabilities will always add up to 1. 3/4 plus 1/4 equals 4/4, which is 1. So complementary probabilities add up to 1. And that's one thing that we've got to remember. And that will help us do some problems that are very complicated. Now the next 3 problems that I do won't be that complicated, but it will get us used to complementary probabilities. So let's take a look at problem number 3. These are some miscellaneous problems. If the probability of winning a certain game is 5/26, then what is the probability of not winning the game? So let's take a look at what we have here. We have winning a certain game, and then not winning the game. I mean, we have this one, if you win a certain game, and then sort of the negation, not winning the game. Those are complementary events. Their probabilities are called complementary probabilities, and we know those complementary probabilities add up to 1. So the way we can do this problem is by going 1 minus this probability. I was thinking about saying, you know, this probability plus x equals 1 and then subtracting, but then we'd start turning this into algebra, and we don't really need to do that here. What we want to do to compute this is to write 1 as 26 over 26 minus 5 over 26. Okay, so now I just have to go 26 minus 5. That gives me 21. This is divided by 26. So it looks like we have it here. This is 21 over 26. That is the probability of not winning the game. And we were able to get this from this probability and going 1 minus it. So that's what we'll be doing a lot of in this section. And you're going to be doing this again and again. There's a quick way when you have to go 1 minus a probability. The quick way of doing this would be for you to go 26 minus 5 in your head, which is 21, and then put it over 26. So that will always work when you have 1 minus a probability. Okay. Now, that won't always work, will not always work if there's like another number besides a 1, like a 7 or something, then we can't always do that. But when it's 1 minus a probability, which is all we'll be doing in 7.4, that will work. You'll see me do that again. Okay, if the probability of no rain is 35%, so here's an event right here, no rain. What is the probability of rain? You could probably have done this problem before you even enrolled in this class. So what you want to do is figure this out. Now some of you might go, I'll go 1 minus 35%. Well, yeah, we are kind of doing that, but 35% is really what? It's 35 over 100. So this is one way of doing this. And then we're going to go 1 minus that. So really all I have to do is go 100 minus 35. 100 minus 35 is 65. It's going to be 65 over 100. Now, we could reduce this fraction, so if we're going to keep our answer as a fraction, we would have to reduce this fraction. But the deal is, I'm going to just change this back to a percentage. So this is 65%. Okay. Because they gave me the probability in terms of a percentage, I give my answer in terms of a percentage. Now, if you'd like to reduce that, you can do that. That's up to you. Another way of doing this problem is you could have just said 100% minus 35%. Because 100% is 100 over 100. That's what that means. And you end up getting that answer. Okay, our next problem has to do with playing poker. If the probability of being dealt a 1 pair, that's a kind of hand you can have in poker, in a poker game is about 0.42, then what is the probability of not being dealt a 1 pair? Okay, So we could just go 1 minus this probability. Now, if you like the fractions better, I'll go ahead and do it the fraction way. This is 1 minus, what is 0.42? Isn't that 42 over 100? Some of you might not prefer this way, and I'll go ahead and write out the blue way after. So really, you're going to go 100 minus 42. 100 minus 42 is 58 over 100. 58 over 100 is 58%. So that is the probability of being dealt one pair in a poker game. Now, if you'd like, you could have gone like this. You could have gone 1 minus 0.42. And then you could have gone 1 minus, line up your decimals, 0.42, and then borrow. You'd end up getting 0.58, which is an acceptable answer, which is 58%. So if you want, you can write this, because we did write it as a percent, didn't we? But we could have just said that this is 0.58 as well. Okay. And maybe most teachers would prefer this because the given was written as a decimal as well. Both are acceptable. You can even go 58 over 100 and reduce that and write it as a reduced fraction. But do you see that all three of these problems were given a probability and were asked for the complementary probability? So look, this is being, I didn't circle this in red, being dealt a one pair, and then this is not being dealt a one pair. So those are complementary events. Now some of you are interested in poker. Let's see if I can find this. Yeah, here it is. So what I'm going to do with the PDFs for this lecture is I'm going to include this near the end of our PDFs. And this is getting all sorts of things. So here's a one pair right here, which approximates to 0.422, etc. And look, there's combinations on the top, combinations on the bottom, and you can go through all your significant poker hands and find out probabilities. So I'll include this. We're not going to go over this. It goes above and beyond the minimum standards for the class, but some of you might enjoy looking this over and looking at the combinations. Let's go ahead and do some more problems now. Okay, a box contains 3 red marbles, 3 blue marbles, and 2 green marbles. So why don't we go ahead and draw this. 3 red marbles, 3 blue marbles, and 2 green marbles. There's the box. So here's the deal. What is the probability that you don't get 2 red marbles? So why don't we go ahead and write this out here. The probability you don't get 2 red. Okay, so this problem right here, it's a tough problem because you don't get 2 red marbles means you can get like a blue and a green when you do this experiment. But it also means that when you do this experiment, you can get a red and a blue, okay? Or a green and a red. So this problem right here is, I'll say it, this is a tough problem if you were just to do this directly. Probability you don't get 2 reds. So what we want to do on problems like this is we want to consider the negation of you don't get two reds. What is the negation of you don't get two reds? You do get two reds. So I'm going to go ahead and use a different color. I'm not going to use red, I'll use blue. And write the negation, which is two reds. Okay, this right here is the complementary event of you don't get two reds. And this is the type of problem we were doing in the last section. You're going to pull out of this box. Now notice what it says here. It says with replacement. Now you might be thinking, well, does order matter, or is it not necessarily in that order? We don't care because it's all of the same color. So I'm just going to do in that order, one probability at a time. What is the probability you pull out your first red? Well, 3 out of 8. Okay, you pull the red out, you put the red back in because this is with replacement. What is the probability you pull out a red from that box? Well, 3 out of 8. Can we reduce anything before we multiply that together? And the answer is no. 3 does not cancel with the 8. So we're going to go ahead and multiply the tops together. 3 times 3 is 9. And the bottoms, 8 times 8 is 64. Okay, 9 over 64 happens to be this probability. So now we're going to find the complementary probability and get our original answer. So that's what I'm going to do. I'll write it underneath here. Whoa, what are you doing, orange? I'm going to go ahead and go 1 minus this probability, 9 over 64. So this is where it really helps to watch the video, because if someone just says, I'm not going to watch the videos, I'll just look at the PDFs, you won't see the order of which I did this. Okay, so now I'm going 1 minus a probability. I just have to go 64 minus 9, which gives me 55. That's the fast way of doing 1 minus a probability, all over 64. And I'm going to tell you a little theorem of number theory and probability. When you're doing complementary probabilities, if the complementary probability is reduced and you go 1 minus that, then this one will also be reduced. Okay? So our probability and its complementary probability, or you can say here's a probability and its complementary probability, will always have the same denominator. So there's our final answer, 55 over 64. Could we have done this problem directly? Yes, but we would have had to break it up into a few cases, and then you would have had to add the cases at the end, and it would have been a little messy. You would have got the same answer, but it takes longer. I guarantee you we're going to do ones that are even tougher that you will not want to do directly. So let's go ahead and go to problem number 7, which kind of has the same setup with 3 red marbles, 3 blue marbles, and 2 green marbles. Okay, so there's the next one. And compare. It pretty much looks the same, except we're asking about like not getting 2 green marbles, but it says without replacement, so that WO is shorthand for without. On the test I would write it all out, okay, but in these notes I don't know why I didn't write it all out, since, oh well. So this is without replacement. So let's go ahead and draw that same box that we drew before. I put the 3 reds, 3 blues, and the 2 greens. Draw the box. And let's write out our question. What is the probability that you don't get 2 green marbles. Okay? You don't get, that's an apostrophe there, 2 green. Okay, once again, a very tough problem, because you don't get 2 green means you can get like a red and a red, or a red and a blue, or a blue and a red, but it also includes you can get a green and a blue, or you can get a red and a green, or a blue and a green. So there's lots of cases to cover with this. So that's what makes this problem more challenging than problems from the past. So what we're going to do is we're going to consider the complement event, the complementary event. And so I'll write this in blue. What is the probability? What is the negation of you don't get 2 green? You do get 2 green, or we'll just say 2 greens. So let's take a look at what happens. How do we do this problem? Well, what's the probability you pull 2 greens out of this box? This is without replacement. So, what's the probability you pull the first green out? So we can do this in this order because it's all the same color. So the probability you pull a green out is 2 out of 8. Now, this is without replacement, so guess what I'm going to do? I'm going to cross out one of the greens. Now, how many marbles do I have in the box? Because this green's like sitting out. I just pulled it out. I have 1, 2, 3, 4, 5, 6, 7. So the probability you pull the second green out is going to be 1 out of 7. We'll reduce any fractions and then multiply. So the 2/8 becomes 1/4. And then I go ahead and I multiply. So 1 times 1 is 1, and 4 times 7 is 28. Be careful when you're doing your homework or your exam. Some people get so happy when they get here, they're like, let's just box it. We're not done yet, but we're almost done. We've just found the probability of the thing that we don't want, which was 2 greens. So now let's go ahead and not put 1 over 28 there, but we're going to go 1 minus 1 over 28. And since it's 1 minus a probability, I'm going to go 28 minus 1. This gives me 27 on the top, and then we have 28 on the bottom. So it's pretty likely that you're not going to pull out 2 greens in this experiment without replacement. So that's our final answer. So this is the way complementary probability works. It helps us solve some really complicated problems. So once again, we can just label this one again. This is a tough problem to do directly, but when you use complementary probability, there it is. It's done like that. This is what you'll be doing in your homework. Let's go ahead and do a different kind of problem, one without marbles. So let's see if I can find it here. Oh, here it is. You spin the spinner 4 times. So here's your spinner. Assume the pointer does not land on a border. So if you like marbles in a box, the marbles are 1, 2, 3, 4. You would pull from this box 4 times, and this would be with replacement. That's if you liked the box. Let me make these look like marbles here. Okay, what is the probability that you spin a repeated number in the experiment? So let me go ahead and write that out sort of shorthand. Probability you get a repeated number. Okay, so what does that mean? Like, when you do this experiment, like, you can get like a 1, 2, 4, 2. So this was the first spin, the second spin, the third spin, the fourth spin. That would be something that you would like. Or 3, 4, 3, 3. There's a repeated number. Or even a 2, 2, 2, 2. But something that you would not like would be like a 3, no, that's a 1. A 1, 3, 2, 4. Why is that something you don't want? Because they say you want to spin a repeated number. So this is something we wouldn't want. This is a very tough problem. The probability of getting a repeated number is a tough problem. But something that's not so tough is the complementary event. The probability of no repeats. And we kind of did a problem like this in the last section. So the probability of getting no repeats, so on your first spin, you can get anything. You can get 4 out of 4. Okay, so suppose your first spin was a 1. Then your next probability is going to be different. The next time you spin, you do not want a 1. So what is the probability that you do not get a 1? It would be 3 out of 4. So suppose the next time you went ahead and spun that, you got a 3. Well, now on your third spin, you wouldn't want to get a 1 or a 3, which means you would want a 2 or a 4. The probability of that happening is 2 out of 4. And it really would help if you have watched the last video from 7.3. Okay? So suppose like you went ahead and the third number was a 2. Well, then the last number, if you want no repeats, would have to be a 4. And what is the probability of doing that? It would be 1 out of 4. So then you would get a 4. And I went ahead and listed this one right here, which has an X through it. We're figuring out the probability of the things we don't want. Let's go ahead and figure out what this probability is. I'm going to reduce fractions. 4 out of 4 becomes 1 out of 1. 2 over 4 is 1 over 2. I have a 3 on the top, and that's not going to cancel with anything on the bottom. So it looks like my top is going to be 3, and the bottom, see, I could be saying numerator and denominator. Shame on me, I'm a math teacher and I'm saying top and bottom. So let's continue. The bottom will be 8 times 4, which is 32. That's my complementary probability, and the one that I want is the probability that's going to be 1 minus that. Okay, so once again, the quick way of going 1 minus a probability is going 32 minus 3, which is 29, and then we keep this denominator, 29 over 32. And you can see each time we do these problems that these two probabilities add up to 1. So when I do this experiment and spin the spinner 4 times, my probability that I spin a repeated number is 29 over 32, which is very likely. And if you did this experiment, like you had a spinner that was like this and you did it again and again, you'd find that most of the times you would get a repeated number. Let's go ahead and do the same experiment where we spin the spinner 4 times, but we'll change the probability around now. We'll change the question. What is the probability that you spin at least 1 4 in the experiment? So that's different than spinning a repeated number. Both of these problems are going to help us with some classical probability problems. One of them having to do with birthdays and 30 people in a room, and another one of these problems is going to have to do with Demir's problem that Pascal and Fermat solved, and thus the whole theory of probability was put on the map. So let's go ahead and do this one right here. And at any time you can pause the video and say, maybe I want to take a shot at this one here, and that wouldn't be a bad idea. What is the probability that you spin at least one 4 in the experiment? So let me go ahead and shorten that a little. The probability of at least 1 4. Okay. So what does that really mean? The probability of at least 1 4, it means 1 4 or more. So it could be like 4 1 2 1, or 1 2 4 4, or 4 4 3 4. Those are things that we would want. Things that we would not want is something that at least 1 4 is something that wouldn't have 4s, like 1 3 2 1. So this 1 3 2 1 is something that we would not want. This right here is a very tough problem. So I'm going to go ahead and take the negation of at least 1 4. At least 1 4 would be getting no 4s. So let's see if we can do this problem. Now I could draw the box with the 4 marbles and say 4 times with replacement. I'm not going to do that. What is the probability you spin the spinner and get something that is not a 4? Well, 3 out of 4. Okay, because you can get a 3, a 2, or a 1, so that's 3 out of 4. Okay, do it again. You're spinning 4 times. Well, that would be 3 out of 4. Do it again. 3 out of 4. And then the 4th time, 3 out of 4. So that's how you get no 4s. 3/4 times 3/4 times 3/4 times 3/4. That's why people invented exponents, because they can say 3/4 raised to the 4th power. But we're not going to do that. Does anything cancel? No. So we're just going to have to go 3 times 3 times 3 times 3, or this is a 9 times another 9. So on the top we end up getting 81. On the bottom you get 4 times 4, which is 16. 16 times 4 is 64. 64 times 4, let's go ahead and see what that is. 24, 25. Well, that's 256. Okay. And resist the temptation of boxing that and calling that your answer. What you want to do, this is our complementary probability. We want to go 1 minus that. So 1 minus 81 over 256. So really, to do this quickly, I just have to go 256 minus 81. So 6 minus 1 is 5. I have to borrow, or I could just say 25 minus 8. 25 minus 8 is 17. So this is going to be 175 over 256. And we know this one's reduced here because this guy is reduced. And so the theorem says that both of them will then be good enough. So this is our final answer right here, the 175 over 256. Let's go ahead and do another problem. Now we're going to go ahead and do a problem that is getting us ready for the birthday paradox. Randomly choose 3 people and look at the day of the week each was born. What is the probability at least 2 of them were born on the same day? So notice this is, we have an at least, and notice in the last problem we also had an at least. Okay? But it's going to be one of these problems that it's going to be modeled with. So we have to know what at least means. Let's go ahead and do this problem. Okay, you're selecting 3 people and looking at the day of the week they were born. I'm going to draw a box and put the days of the week in the box. And we've done stuff like this before. So here's Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Since I'm choosing 3 people, what I'm really doing is I'm selecting from this box 3 times. Now, is it going to be with or without replacement? Could 2 of these 3 people have the same day of the week that they were born on? Yes, they can. So this is actually with replacement. And what they want to know, what is the probability at least 2 of them were born on the same day? Here's another way of looking at this. What is the probability of doing this experiment and getting a repeat? Okay, so we have these 2 problems. The problems 8 and 9, and 9 did have an at least in there. But number 8, look at this. Probability, repeated number. 4 times with replacement. Notice, 3 times with replacement. Probability, I just put repeat, but I could have also said repeated day or repeated marble. So it's going to be, this one's going to be like problem number 8. Okay? The numbers are going to be a little different, but it's going to be kind of the same theory. This is a tough problem. Figuring out the probability that you get a repeat when you draw from this box 3 times with replacement. So what am I going to do? I'm going to go ahead and do the complementary event, the probability of that. And the probability of the complementary event, so this is going to be the probability of no repeats. Or we could say no reps. Okay, so we're trying to get no repeats. What's the probability? What could the first probability be? Well, the first probability, it doesn't matter what you pull out of the box the first time. You have a chance of getting no repeats. So you've got 7 out of 7. So suppose we pull a Friday out of the box. Okay, well, the next time, since we're trying not to get repeats, we do not want to pull a Friday out the next time. So we pull the Friday out and we put the Friday marble back in. So what's the probability we get something that does not repeat with Friday? Well, that would be 6 out of 7. So suppose you pulled a Monday out. You put the Monday back in because this is with replacement. And the third marble you pull out of the box cannot be Friday or Monday. So what's the probability of pulling something out of this box that is not Friday or Monday? Well, that leaves us with 5 out of 7. We'll go ahead and reduce our fractions. 7 over 7 becomes 1 over 1. Nothing else reduces or cancels. And so I get 30 on the top by going 6 times 5, and on the bottom, 7 times 7 is 49. Okay, so that's not my final answer, but I'm almost done. The probability of getting a repeat would be 1 minus this probability. 1 minus 30 over 49. So really all you have to do is go 49 minus 30, which is 19. 19 over 49, and that gives the answer. The probability that at least 2 of them were born on the same day, or the probability you get a repeat, and that's what it is. So, what day of the week were you born on? Do you know that? So, how about what I can do, I know I have it somewhere, is with the PDFs, there's this little way you can find out without taking out your cell phone. That's kind of cheating, but I guess maybe you'll do that. But there's another way of doing it where it's all mathy, and you can walk through a few steps, and it will tell you what day of the week you were born on. You might know your birthday, but you might not know, like, was I born on a Wednesday or on a Saturday, and you can figure that out, and I will include that as a PDF. It has nothing to do with figuring out this probability, but it's, you know, you can figure out the days of the week when things happen in the past or in the future when things will happen, you know, without taking out calendars or, you know, looking at your cell phones. So that is number 10, and we've kind of reached a high point in the class, because now we're going to do a famous problem. So this is our puzzle. Remember, you're in a room with 30 people. What is the probability that at least 2 of these people have the same birthday? Ignore leap years. That's actually going to help us. If we did it more technically, including leap years, we would get pretty much the same answer, especially when we round it. So we're going to ignore leap years, and we will round our answer to 2 decimal places. That's what we'll do. So let's go ahead and do this problem. I'm going to go ahead and draw a box. And in this box, I'm going to put 365 marbles. So the first marble being January 1st. The second marble being January 2nd. And I'm not going to draw all the marbles, but you know that the last marble will be December 31st. And it kind of reminds you of this problem right here, number 10, where we had 7 marbles in the box. Instead of looking at birthdays, we were just looking at the day they were born, Sunday through Saturday. Now we're looking at birthdays. We have 3 people here. Over here we have 30 people. So it's pretty much the same problem with different numbers. There are 365 marbles in the box. We are going to pull marbles from this box 30 times. And this will be with replacement. With replacement because 2 people can have the same birthday, like an April 5th and an April 5th. And so that's how we're going to approach this problem. We'll write out the probability. What is the probability at least 2 of these people have the same birthday? So the probability that you're going to get a repeat. Well, that's a tough question. So we're going to go ahead and look at the complementary event. That would be the probability of no repeats. And once again, I hate to keep bringing back this problem, but this problem is pretty much the same. Look, no repeats, repeats. We did the same thing with the days of the week, except now the numbers are going to be bigger. So let's continue with this problem. Well, no repeats means the first time I pull a marble out of this box, it could be anything. It could be 365 out of 365. So suppose I pulled May 4th out of the box. Then the next time I pull a marble out of the box, I would put May 4th back into the box. The next time I pull a marble out of the box, it could not be May 4th. So the probability of that happening would be 364 out of 365. So let's say the next marble I pulled out of the box was December 25th. Pull that marble out, put it back in. That would mean that the next time I pull the marble out of the box, it could not be those dates there. So that would be 363 over 365. And so on. Well, how many fractions or probabilities am I going to have? I'm going to have 30 because that's how many people I have. So to make things a little bit more condensed, The bottom says 365 times 365 times 365 times 30 times. So it's going to be 365 to the 30th power. And that's why there's a calculator icon there. The top says 365, 364, 363, 362. Does that remind you of anything? It reminds you maybe of a countdown which we covered in the last chapter. This is a permutation. So instead of writing the P, I'll write P-E-R-M so we don't confuse that with probability. Permutation, 365, pick 30. So our countdown only has 30 numbers because right here there's 30 fractions. Well, this right here I can do on a computer or a calculator, and I'm not going to take the calculator out and show you how I push the buttons on here, but when I did this and I rounded the answer, I ended up getting 0.29. So now we go back up here, because here's the original question. What is the probability you get a repeat? I'm going to go 1 minus 0.29. You could say 100% minus 29% or whatever. However you get this done, you're going to end up getting 0.71%, which completes our problem. This problem has a surprising answer. If you're in a room with 30 people, the probability that at least two share the same birthday is 71%. Seems unlikely, but it really is true. So, because this plays with our minds, some people have called this the birthday paradox. Now, there's not a contradiction here. Paradox has a few different meanings. In this case, paradox means the truth standing on its head to get attention or whatever. But the deal is, it's not what we think it was going to be. We didn't think it would be 71% of the people are going to, 71 not percent of the people, but 71% of the time when we do this experiment, there's going to be at least 2 people sharing a birthday. It just does not seem like that would happen, but it really does. So if this were a face-to-face class, what I would do is I would then go around the room asking maybe a class of 40 people or 30 people what their birthdays were to prove that, well, they wouldn't prove it, but that lots of times I would get repeated birthdays in a class of 40 people. But we can't do that. We cannot do that. So what I did is I generated birthdays or days of the year with a random generator, and I'll show you the results. So here it goes. The first time I did this, we'll call this experiment 1. Those are 30 birthdays. And look, I ended up getting a repeat there on December 9th and also December 1st. So these are randomly generated. So in this case, we got a repeat, and it's 71% chance that we would. Experiment number 2, or we could call it trial number 2 as well. I generated 30 random birthdays and I did not get a repeat. Now you might go, aha, Joe, it goes against the math. No, it doesn't. There's a 29% chance that this will happen. Okay, trial number 3. I went ahead and did this again, and look at the these are random birthdays. I got a repeat. I got September 20th, and then look, February 17th popped up 3 times. Trial number 4. I ended up getting repeat, December 27th and June 27th. Trial number 5. I ended up getting Repeat. 3 different times that happened on March 16th, August 22nd, and December 18th, and these are all randomly generated. Trial number 6, I end up getting repeats. September 11th, 2 times, and August 21st, 2 times. Trial number 7, and we would expect this if we're doing so many trials. Look, this time I didn't get any repeats. And there's a 29% chance that that could happen. And then the last one, because I was getting sick of generating random birthdays, this was trial number 8, and I got a repeat on April 9th. So 6 out of 8 times, I ended up getting repeats in birthdays. And that's like 6 out of 8 is like in the 70% range, or somewhere in the 70s, and that kind of is close to 71%. Now if I did this, if I did 1,000,000 trials, it would come closer to 71% of the time where I get repeats. And then we're talking about a statistics classroom. So if you're interested, well, what would happen if it was a different number of people in the room? You could actually do this. You could replace that 30 with, a 20 and do the calculations. I'm going to include in the PDFs something that looks like this. It's going to actually be neater than this. But this shows you that if you have 23 people in a room, the probability at least 2 of them will share a birthday is about 50%. And that's 23 people. So look, if 1 person's in a room, you're not going to have at least 2 people sharing a birthday. That's why that one's 0. And so you have all the numbers. Look, if there's 40 people in a room, it's 89% chance that 2 of them are going to share the same birthday. And then 50 people is 97% chance. So this seems to be something, maybe this shocked you that this happens. That's why it's called the birthday paradox. But in cryptography, people will often use this. They'll call it the birthday attack, because you attack some cryptography to see if you can break the code, and it's called the birthday attack, and it's very popular in cryptography. And instead of having 365 marbles, maybe there's 1,000 or 10,000 marbles, and then you try to get a few matches, and if you do, then you can break the cryptography. So there's more applications to this than just going, wow, that's neat. If you understood this birthday paradox problem, then you are doing a better job than I was in college when the professor presented this to us. The professor did this problem, and instead of 30 people, it was N people, and I was looking at my friends in the class, and we didn't understand what was happening. So if you can understand what we did here and it makes sense, you're doing a better job than I did. Let's go ahead and do another problem. So before we get to the puzzles, this is our last problem, and it was actually our first problem that we did in probability. I kind of introduced Demir's problem to you. He was the gambler, and he couldn't get this problem done. We're going to roll a die 4 times. What is the probability of getting at least 1/6? Round your answer to 2 decimal places. So rolling a die, 1, 2, 3, 4, 5, 6. We're going to roll the die 4 times. So I'm pulling marbles out of the box 4 times, and this is with replacement. We are asked, what is the probability of getting at least 1/6? So that's a very difficult problem. Demir couldn't do it, and this is what Pascal and Fermat did. And they corresponded through letters to each other. Well, we're going to look at the complement. What is the complement of at least 1/6? No. 6s. So this might look familiar. I'm trying to find the problem now. Oh, here it is. We did a problem that was similar, it was a spinner, so there were 4 marbles instead of 6. We were spinning it 4 times, just like 4 times here. And we were asking the same question, what's almost the same question. You want at least 1 4. Well, now we're doing at least 1 6, and so we're doing the same sort of deal. This was the problem that put probability on the map. Let's see if we can do this. Well, what is the probability of reaching into that box and not getting a 6? It would be 5 out of 6. So you put that marble back in and you do it again. 5 out of 6. Then you do it again. 5 out of 6. And then you do it one last time. 5 out of 6. Nothing cancels. So I have to go 5 times 5 times 5 times 5. So 5 times 5 is 25. Times 5 is 125. Times 5 is 625. I also have to go 6 to the 4th, or 6 times 6 times 6 times 6. So 6 times 6 is 36 times 6. 36, carry the 3, 18, 19, 20, 21. And then times 6 one last time here. 36, 6, 7, 8, 9, and then we have 12. So this is a 1296. This is not my final answer. What my answer is going to be is I'm going to go 1 minus this probability. Okay, so this is 1 minus 625 over 1296. I'll go ahead and do the arithmetic over here. I did put a calculator on this problem, but I'm really not using a calculator as I'm writing it out here. 6 minus 5 is 1, 9 minus 2 is 7, and 12 minus 6 is 6. So it looks like the top of the fraction is going to say 671 over 1296. There it is. They said round to 2 decimal places, so we might as well, you know, I put this in a calculator. I ended up getting 0.52. So that is how you do this problem. It's a historical problem because it is the one of the problems that put probability on the map. They got Fermat and Pascal interested in probability and discovering things about probability. Let's go ahead and take a look at our puzzles. What goes in the box? Okay, well, if you're taking a look at things, we have this square here, you know, that consists of 4 squares, and if you look at the opposite squares, you have like a minus and a plus, and then over here you have an open circle or a white circle and a black circle. Well, look over here, it's the same thing. This is a right arrow, a left arrow, triangle, and then like sort of the upside down version of that. Okay, so those are opposites, and then over here we have black square, white square, and then male, female. And then over here we have half moon, and they're different directions, so the thing that goes over here is the opposite of that arrow, which is the down arrow. The next puzzle, fill in the missing box. So the solution to this happens to be gotten by reading from left to right, line by line. So watch this. Triangle, and then look. Triangle plus. Triangle plus, I'll call that upside down triangle. So upside down. Triangle plus upside down times. Triangle plus upside down times circle. I'm adding a new symbol each time. Triangle plus upside down times circle, left arrow. Triangle plus upside down times circle, left arrow, square. Triangle plus upside down. What comes after upside down triangle? It's the multiply. And then circle, left arrow, square, and then the new symbol is the up arrow. But that's what goes in the box, that one right there. So that completes our very last section that we're covering, which is 7.4. The next thing that I'm going to do, for those of you who want to stick around in this video, is talk about probability in the Bible. So if you don't feel comfortable with that, you can just stop the video. So these caps right here, there's 1,000 of them. Now where did I get those caps? I got them from these pens. We use these pens in class. So, you know, when the pen would run out of ink, I would take the cap off of it. Okay, and that's a black cap. Okay, so I'll put that back. So I've been collecting them, and inside this box we have 999 black caps and 1 red cap. And so what we're going to be doing with the probability in the Bible is all going to be on PowerPoint, but we've got this big box and it's a huge box that contains 1,000 of these pen caps, and we're going to be talking about pen caps, probability, and prophecies. So we'll switch it over to the PowerPoint. Messianic prophecies. Okay, what is that? A messianic prophecy is a prediction, prophecy is prediction, relating to the Messiah. And the Messiah was the expected deliverer for the Jewish people. Well, Jesus is a man from history who fulfilled hundreds of messianic prophecies. Therefore, he is regarded as Messiah by Christians. First of all, Jesus did walk on this earth 2,000 years ago. I can find lots of atheists who would agree with that. In fact, there were 17 non-Christian historians who wrote about the death of Jesus by crucifixion. Secondly, Jesus appeared on the scene hundreds of years after the prophecies were written down in the Old Testament. And we have the Dead Sea Scrolls, which were discovered in 1946, that kind of verifies that, one of the verifications. They were written down around 200 BC. That was before Jesus came on the scene. Before the Dead Sea Scrolls were discovered in 1946, the most ancient Hebrew Bible documents came from around 900 AD. And the funny part about it is the Dead Sea Scrolls were virtually identical. And they were written around 200 BC, not 900 AD. The third thing that we want to look at is, we'll assume the New Testament is reliable. We can verify this. There are thousands of manuscripts that exist for the New Testament. There are more manuscripts that exist for the New Testament than any other ancient document. The manuscripts of the New Testament are closer in age to the original than are any other ancient document, and the New Testament documents are more accurate than any other ancient document. So let's go ahead and get to the probability part. Before we get to the probability part, I want to set this up. A while ago, there was a professor named Peter Stoner, and he was from Westmont College. He took 12 different classes, that's about 600 students, and he calculated probabilities of 8 messianic prophecies and published the results in a journal. So let's take a look at these 8 messianic prophecies. There they are. So these are predictions from the Old Testament: Zechariah, Micah, Malachi, Isaiah, Psalms. Those are all Old Testament books, and they had predictions about the Messiah. So there's 8 predictions here. And Jesus comes along in the New Testament and he fulfills all 8 of these predictions. Now, there were more than 8 predictions in the Old Testament, but we're just picking 8 because that's what this study did. We're going to analyze 8 of these prophecies. The Messiah will be betrayed for 30 pieces of silver. And that's what happened to Jesus. But what they did, what the class, Peter Stoner's class did, is they asked, what is the probability that a random person fulfills that prophecy? The students came up with 1 over 10,000. Now, Dr. Stoner knew there would be skeptics critiquing the numbers, so he changed the probability. So he did that. We hate when math teachers take out the red pen and do that. He changed it to 1 over 1,000. So he made the denominator of the fraction smaller, therefore making the probability bigger or more likely. And he did this because he knew people would be critiquing these numbers. So he made a more conservative estimate of the probability. How likely would it be for you to be betrayed for 30 pieces of silver? Pretty unlikely. We had that box that had the pen caps. So here they are there. It would be the probability of closing your eyes and reaching into that box and pulling out the red pen cap. It's not very likely. And in fact, since these are conservative probabilities, the box of pen caps would have to be a lot bigger for it to represent the true probability of being betrayed for 30 pieces of silver. The next prophecy, the Messiah will be born in Bethlehem. It's hard to control where you are born, so they did distributions of the land. This is what the class did. And they estimated it to 1 over 280,000. But Stoner made that probability bigger as well, and he said it's 1 over 100,000. A messenger will prepare the way for Messiah, 1 over 1,000. Of course, that refers to John the Baptist. The Messiah will enter Jerusalem as a king riding on a donkey, 1 over 100. Messiah will be betrayed by a friend and suffer wounds in his hands, 1 over 1,000. The betrayal money will be thrown down in the house of the Lord and will go to the potter. That's very specific. And that happened, 1 over 100,000. Messiah will remain silent while he is afflicted. Usually people try to defend themselves. So the probability of that happening is 1 over 1,000. And Messiah will die having his hands and feet pierced. 1 over 10,000, that came from Psalms. And this was before crucifixion came the big deal. So that was long before we had that. So this is what we're going to do. We are going to multiply those 8 probabilities together and get 1 over a 1 followed by 28 zeros. Or we can say 1 over 10 to the 28, which has a name, 1 in 10 octillion. And this is the chance of one man fulfilling all 8 of these prophecies. Now, the total number of people who have lived since the time of these prophecies is less than 100 billion. So I'm going to multiply that probability by 100 billion, and it's actually going to make the numerator bigger. But that's going to give me the chance of any man fulfilling all 8 of these prophecies. And that's going to be 1 over 10 to the 17th, which has a name, 1 in 100 quadrillion. And that is a conservative estimate. This probability should be 1 over a bigger number than 100 quadrillion. Okay, so it should be more unlikely. Let's go see what 100 quadrillion is. So even if you're not a big fan of the Bible, you will find this interesting about the number 100 quadrillion. Suppose we take 100 quadrillion black erase, did I say black erase? 100 quadrillion dry erase black pen caps and lay them on the face of California. We're going to assume the lakes and the rivers are dried up or frozen, and we're going to do this. It will look like that. So you notice I even put some on Catalina Island and some of those other islands. That's 100 quadrillion caps. How many caps does that happen to be? Well, these caps will cover the state 5 feet deep. Actually deeper, but we'll just say 5 feet deep. Now we're going to take one red pen cap and place it anywhere among the black pen caps. You can mix it up all you want, and then you're going to blindfold a man and tell him he must pick up just one pen cap. He can walk anywhere he wants in California before picking up one pen cap. So I can imagine this guy's he's just walking through the state of California, stopping anywhere, picks one pen cap without looking. The chance of him picking up the red cap is the same as the chance that the prophets of the Old Testament provided the 8 messianic prophecies from their own wisdom and not God's, and having them all come true in any man from their day to present time. And only 8 prophecies were chosen for this experiment. There were hundreds of fulfilled messianic prophecies. So sometimes people say, well, why are you a Christian? Is it just blind faith? Why did you pick that? It's because we have evidence. We have predictions in the Bible, and we see the predictions coming true. And that's what seals the deal for me. No other religion offers that kind of pattern, with predictions made, and then later on the predictions coming true. I'll include the handout for this with the PDFs. We are finished with Chapter 7 of Probability. Have a good day. I'll see you in the next video.